Have you ever heard of a universe that runs on just 4 simple rules? Well, today, we're diving into one of the most incredible things ever created in computer science, Conway's Game of Life. It's a system that completely messes with our ideas about what life is, where complexity comes from, and what it even means to compute something. So let's peel back the layers on this little digital universe and see what secrets it's hiding. Now, here's the really weird part about the Game of Life. It's a zero-player game. Yeah, you heard that right. You just set up the board, you press start, and that's it. You just watch. From that very first moment, the entire future of this universe is locked in, completely predetermined. And yet, what grows from that simple start? A world of unbelievable, totally unpredictable complexity. And that right there, that's the big question we're going to unpack today. How on earth can a system with just a handful of rules create things that seem to live and die and move across the screen, and even build other things? It sounds impossible, right? Well, let's find out. Okay, so first things first, we need to get our heads around the environment where all this magic happens. The best way to think about it is like a digital petri dish, an entire universe laid out on a simple grid. The fancy name for this setup is a cellular automaton, but really, it's a simple idea. It's just a grid, right? And every single square, or cell, can be in one of 2 states, either alive or dead, on or off. And with every tick of the clock, each cell makes a decision. It looks at its 8 immediate neighbors, up, down, left, right, and the diagonals, and based on what it sees, it decides if it's going to be alive or dead in the very next moment. And here they are. This is the entire secret sauce. The physics of this whole universe, the entire algorithm for existence, is boiled down to just these 4 simple rules. This is what governs all life, death, and everything in between. It really is all about balance. First, think of it as a loneliness. A live cell with fewer than 2 neighbors dies. It's just too isolated. But then there's overcrowding. A live cell with more than 3 neighbors also dies. The sweet spot for survival is having exactly 2 or 3 neighbors. And finally, birth. A brand new cell springs to life in an empty spot, but only if it has exactly 3 neighbors. That's it. 4 conditions. That's the entire playbook. Okay, so this is where your brain starts to melt a little bit. The system is 100% deterministic. If you know the starting pattern, the entire future is set in stone. But, and this is a huge but, it's also what's called computationally irreducible. There is no shortcut. There's no fast-forward button to see what happens a million steps from now. The only way to find out is to run the simulation and let it happen step by agonizing step. So we've got the grid, we've got the rules. What actually happens when you just let this thing run? Well, you don't just get a bunch of random flickering. You get an ecosystem, a whole digital zoo filled with amazing, complex patterns and creatures. And these patterns, they fall into these really distinct families. You've got your still lives, like the block, which are basically just stable rocks, they never change. Then you have oscillators, like the blinker, that pulse back and forth in a perfect rhythm. And then things get really interesting. You get spaceships, patterns that actually pick themselves up and move across the grid, and then you get guns. Now, of all the creatures in this digital zoo, one is more important than all the others combined. The glider. This tiny little 5-cell pattern is, without a doubt, the biggest discovery in the Game of Life. It's a little spaceship that moves diagonally across the grid, forever. It's like a little packet of information, a messenger particle carrying a signal across the empty void. And that discovery led to something even more mind-blowing. In 1970, a guy named Bill Gosper found this, the glider gun. Just look at it. It's a stable, pulsing engine. It has a perfect rhythm of 30 generations. And every time it pulses, it shoots out a brand new glider that flies off into infinity. It's a factory for information. You have to understand, this was a massive, massive deal. John Conway, the creator, had put out a challenge. Could a small, finite starting pattern lead to infinite growth? For a while, no one knew. The glider gun was the answer. It was the definitive proof, a resounding yes. A small machine could create infinite complexity forever. But believe it or not, infinite growth was just the tip of the iceberg. It was the key that unlocked the deepest, most profound secret hidden inside those 4 simple rules. a ghost in this digital machine.
So this whole phenomenon we've been watching, it has a name. It's called emergence. It's this beautiful idea where incredibly complex behaviors, like a glider purposefully moving across a screen, just emerge from a bunch of simple local rules. The whole becomes so much more than the sum of its mindless little parts. Now, to get nerdy for just a second, scientists talk about two flavors of this. There's strong emergence, which is the wild idea that completely new physical laws could pop into existence at higher levels of complexity. The game of life is what we call weak emergence. All that amazing complexity was technically possible from the start, hidden within those four rules. We just couldn't see it until we let it run.
But what is the ultimate thing that emerges from this system? What is its final, most incredible secret? It's this. The game of life isn't just a cool screensaver or a simulation. It is a fully functional universal computer.
That means it's Turing complete. That's a fancy way of saying it can compute anything your laptop can compute. How is that even possible? Well, remember our little friend, the glider? You can use streams of them as ones and zeros. And by engineering incredibly precise collisions between these glider streams, people have built logic gates, the and, or, and not gates that are the absolute bedrock of all computing. From there, you can build anything. People have built working computers and even a playable game of Tetris inside the game of life. It's just staggering.
So why does any of this matter? I mean, it's a super cool theoretical game from 1970, but what does it have to do with us, here in the real world? Well, the connection is actually way deeper than you might think.
You see, the game of life is part of this long, epic scientific quest. It started way back with guys like John von Neumann, who was trying to figure out how a machine could build a copy of itself. Then you had Alan Turing. Yes, that Alan Turing, who showed how simple chemical reactions could create the spots on a leopard. Conway's genius was in showing just how ridiculously simple those starting rules could be.
And this isn't just a metaphor. These ideas are used today to model real biological systems. Scientists use cellular automata to understand how our cells organize themselves into tissues, how a plant knows how to grow, how those beautiful patterns form on a seashell. It seems like nature, just like Conway, has a real love for simple rules that lead to breathtakingly complex results. Which, of course, leaves us with one last, really profound question to chew on. The game of life is definitive proof that a universe of astonishing complexity, a universe capable of computation itself, can spring into existence from just 4 lines of code. And it just makes you wonder, is the operating system of our own universe, of our reality, written in a similarly short, elegant, and beautiful code, just waiting for us to find it?